Hello, everyone. Today we have Francis Bach again with the second lecture of optimization. So keeping the introduction short.
Okay, so
Stage
let's start. So welcome back. So today I'm going to finish my lecture on optimization. So the slides, which were a bit updated, are still online, either the website of the summer school and also my own website. So let me jump directly to where I left off yesterday, and I will do some small revisions, but small like review. So so let's start there. Okay, so this was typical machine learning optimization problem when we want to minimize a finite sum. So this is true in many areas of learning or signal processing, but in machine learning, this is really related to every function is a loss for a single observation or a mini batch of observations. So what we have seen yesterday is the first class of techniques, which we call batch gradient descent, where you ignore the fact that you have a finite sum and you do gradient descent, you follow the negative gradient. So the convergence rate was dictated by a number called the condition number, which was the ratio between the largest eigenvalue over the smallest eigenvalue of the Hessians. So this was telling us whether the level sets locally look like big balls or elongated ellipsoids. And so it's exponentially convergent, but at every time step, you have to compute the whole gradient, which is costly. And we saw the opposite, which is stochastic gradient, where you don't look at all gradients at every iteration, but just a single one, which you take randomly. So here with replacement. And now every iteration has a much better complexity, independent of n, but you pay this in the convergence rate by having 1 over t or kappa over t instead of exponential in t. And what the goal, and this was the picture, like the naive picture of the two algorithms. So deterministic will be very fast at the end, but slow at the beginning, whereas stochastic will start very fast at the beginning. At the first iteration, as soon as you see data point, you start to do progress, but then that will be a bit slower. And this was the new thing was to be able to get the best of both worlds. So let me skip the writing work. And so what I presented last was a SAG algorithm, which is a simple modification of stochastic gradient, where we take at every time step a random function. Okay, so for machine learning, a random pair of observations, compute the gradient. And instead of just following the gradient of the stochastic choice, instead of choosing following the stochastic gradient, we store it. And at every time step, we assemble the whole gradient, okay, which we call the stochastic average gradient, and we take a step. Okay, so this was the difference with previous work was the fact that we were doing like randomization instead of cycling. Okay, and this is crucial because we can get a big step size. And there was one issue about storage, because since you store gradients, and if you're in high dimensions, you have to store n gradients in dimension d. So if both n and d are very large, it's kind of a problem. And the first solution is for supervised learning with linear models, where the gradients, as we've seen, are proportional to the feature vector. So we don't need to store the entire gradient, but just the derivative of the loss functions. So for those who are used to the SVM dual, this is just the alpha I over there. All right, so in terms of rates of convergence, so this is can be analyzed. And if you assume the regular smoothness assumptions and strong convexity assumptions, then we were able to, among linearly convergent algorithms, which are gradient descent in the accelerated version, we were able to replace the product of n times condition number by the sum of n plus condition number. And since condition numbers typically for machine learning are order n, typically, and sometimes larger, but of order n, then this is like a very significant gain. So here, interestingly, that result beats two lower bounds. Okay, so which I've mentioned at least the one for the full gradient. So for the full gradient, Nesterov acceleration cannot be improved. So if you want to minimize a smooth, strongly convex function, there's no way you can beat this. But here we can beat it because we use the fact that the function that we optimize is a finite sum, and we have access to the elements of the finite sum. Okay, so we leverage more structure and we can improve on the rates. Similarly, for stochastic gradient, the rate which I'm presenting over there is the optimal rate that you can get if you minimize an expectation. This dates back from Nemirovsky and Yudin. So here we can improve upon it because we know we have a finite sum, and we can identify when the function has been selected a second time. So it's key. The storage is really the key aspect. So we can identify, oh, this is a function which I had before, so I'm using this. And the lower bounds that Nemirovsky and Yudin have proved are not using this finite sum aspect. So this is why we can improve the rate significantly. So just as a reminder for a later part in the talk, this is a finite sum because we consider the training error. Okay, so SGD can be applied for the testing error, as I will mention later. So for the testing error, you cannot improve on those rates of SGD, but for the training error, you can. And we'll come back to that like in a few slides. So if it's just convex, so yeah, I don't want to spend too much time, but in most of optimization theory, often you start by proving things for the simplest setup, like strongly convex. And typically you get like exponential convergence and with a rate that will go to 0 or 1, depending on the way you see it, when mu goes to 0. And for the cases where you just convex, so like the super ill condition cases, so either cases where you don't add regularization or cases when mu is very small, then you need to dedicate to have a new analysis. And it turns out that you can have such a new analysis and similarly you obtain some gains. So here the gain is about the square root of n compared to the regular gradient descent. So here one key aspect, and I think I have mentioned it yesterday, is adaptivity. Okay, so gradient descent was adaptive to the difficulty of the problem, or more adaptive to the easiness of the problem. If your problem is hard, it's going to be slow, but there's not much you can do about it. But if it happens to be fast and easy, like strongly convex, and sometimes only locally strongly convex around the optimum, then gradient descent was adaptive and SGD was not. So this new version of SGD is adaptive, and we end up, we have the same algorithm with the step size is of still 1 over L, and the results I'm presenting in this slide and the slide before are with the exact same algorithm. There's nothing to be changed. This is true for those 3 ones. This is not for those 2 ones, gradient and sag. This is not true for SGD. All right. So now a few like implementation details which are like valid, in fact, for both SGD and those fast gradient techniques. So if you have sparse features, which is very common when D is very large, then for SGD it's very simple because you select a single gradient, which is proportional to the feature vector. So a few non-zeros. So you just only update the components for which the gradient has non-zero components. So for SAG, it's a bit of a problem because you take the average gradient. So the average gradient over all the data set will typically be not sparse. So if you want to avoid having like an expensive iteration, you have to do what Mark Schmidt was calling the just-in-time updates. Okay, you just delay the update until you need to do the update. Or there's also a very nice stochastic version to do this by Leblond, Pedregosa, and Lacoste-Julien. Other classical and important detail is the mini batch. You can replace a single observation or a single pair of observation by a mini batch. So typically, this is not very important in terms of rates, but in terms of speed, hardware speed, this makes a difference because you have a block access to data, and typically it's more efficient than doing some random access to data. So I think there was a question yesterday about this. You can do line search also with that SAG algorithm. Okay, so you can look at the paper if you want. And also very important, you can also do non-uniform sampling. So this is not only for SAG or variations of SAG, this is for all SGD. Sometimes some functions are more important than others. Typically, if they vary a bit more, you want to select them more often. And this is possible for SGD. And I think this is a classical notion in optimization. And this also makes a difference in this setup. So we have some software, okay, so I think, so here, and also very classical in optimization. So the SAG algorithm is 2 lines of code, okay, so if you just take the code, the line of code, and do it yourself with the step size 1/L, it's going to be reasonably fast. But if you want to get like super fast, you can get code from Mark Schmidt, where the line search is involved, and this makes it like much more efficient at the end. So let's see some simulations. So this is like classical benchmarks, like in small dimension, high dimension, and quite a reasonable amount of data points. So those are all the competing techniques. Okay, so in all of my plots, this is like number of passes over the data. So here this is written effective because since we do sampling with replacement, after n iterations, we have not seen the entire data set. Okay, so we call that an effective pass. Okay, so after like 40 effective passes, you probably have seen most of the data set. And so the x-axis, number of passes in the regular scale, and on the y-axis, this is distance to optimum or in the logarithmic scale. And so here there are a few methods. Okay, so AFG, this is like accelerated full gradient descent, so Nesterov acceleration. In IAG, this is like the version of our algorithm without cycling. Okay, as you can see, it's not very fast. And in blue and green, this is like SGD. I think SG with a decaying step size and ASG with the constant step size. As you can see, SGD does well in the beginning, but then cannot go very fast. And whereas like the gradient-based techniques, so acceleration, like IAG and LBFGS, which is the Casey-Newton method, they do not as good at the beginning, but then they do better. And similarly here, you can see here even stronger effect of the batch techniques. Okay, they are like a line, they are linearly convergent, but the slope is so weak that you never see really it converging. Okay, so this is really apparent on the right. And now if we add the SAG algorithm, so this is the exact same plot, but we need like to change the scale because we convert like significantly faster. You can see that at the beginning, it starts like a stochastic gradient, but then it gets to be a line, okay? It gets to be a line like that, and you see even more appearing over them. Okay, so in fact, the line here, the slope of the line, and this is a consequence of the convergence rates, which I have mentioned earlier. That slope is, if the condition number is large enough, is small enough, less than n, the slope is independent of n. Okay, so the slope over there, this is typically minus 1/kappa. Okay, this is just a condition number. But here, because we have transformed, we have an improved convergence rate, the slope is typically independent of n. So the number of kappa. So the number of passes typically it does not need to depend on condition number. And you see here, after 30 passes, you have reached machine precision. Okay, so this shows that the what I've mentioned yesterday, which is that we don't need to optimize up to machine precision. Indeed, we don't need to, but we don't really care because like if we wait like a few more passes, we're going to get to very low precisions, very low epsilon. All right, so you see for logistic, so cases where it does not work. Okay, it's very important to see other cases where it does not work. So other data sets like classical benchmark and all the techniques, okay, the names do not matter much, are doing not very well. And SAG, in fact, is doing a bit better, but not really better. And on this one, even like DCA, which is a dual core data set, happens to be to do significantly better. Okay, and so one of the reasons here is that those data sets are have some data points which are big norm. Okay, so you see the cases where you may want to favor non-uniform sampling, And if you do this, then you recover the same type of behavior that SAG is significantly improving over others. So here, what I like to highlight is the difference between before uniform sampling, so in the purple, and after uniform sampling in like greenish blue. So this difference can be quite significant. Okay, so I will come back to that later in the talk. All right, so this is only for the training error. So this is a machine learning summer school, not an optimization summer school. So we have to check. We have to check if it matters on the testing error. Okay, so on the left, this is the same plot as we had before, I think on one of the data sets on RCV1, and you see like SAG reaching like machine precision after like 40 passes, and all the others being quite slow. Okay. So here, for all other algorithms, it's very important, the optimal step size is used. And what I mean optimal is that we tried all step sizes, selected the one which were best, okay, and then plotting only those. Whereas for SAG, we simply use here the step size that is appearing from the bounds, like 1 over L, or sometimes line search. And now it is the testing cost. Okay, so here you see that the testing cost now it's not anymore in logarithmic scale. Okay, it's just the logistic loss. You see that on the test set after one pass, both stochastic gradient techniques, like in blue and green, and SAG are reaching the best test error after one pass or a few passes. So this shows that those improvements on the training data, okay, are not totally seen on the testing data, okay, in the sense that we reach the best testing error a bit quicker, but not a lot quicker, but all methods end up doing it. The stochastic techniques get it quite quickly, but other techniques also are quite slow. So here, what's important is that all the step sizes of other methods were selected as being the best ones. Okay, so this means that to be able to achieve the similar performance as SAG, you need to be able to choose a step size, which is not an easy task. As I've mentioned yesterday, if you mess up with a factor of 5, even in 1D, this could be an issue. Okay, so at the end, the gain in testing errors is, for me, a gain of robustness. Okay, one, and second, it's also a gain in terms of knowing where to stop. Okay, so when you run, like you say you're on the left, okay, you want to run, you want to know where you stop. So which should be the precision that should stop? Okay, should I stop at -5, at -3, at -10? Okay, and so it turns out that with those techniques, you don't need to worry so much. You add a few more passes and you can just simply get like convergence to very high precision and don't need to worry about like, did I optimize enough? So again here, to avoid overfitting, there is regularization. Okay, so here we have added some squared regularization. All right, so like of course we are not the one having worked on this. So we started this with Nicolas Leroux and Mark Schmidt in 2012, but then at pretty much the same time, like the dual algorithms were also available when you had like, a dual problem. And then there were like a sequence of other algorithms with similar rates of convergence and similar iterations. Okay, you go from one to the other by changing a few characters. And I want to mention, I think, one of them, which is SVRG, the work by Johnson and Zheng and colleagues, so there are different Zhengs, who essentially found a way to interpret the iteration in a different way. So what I've shown is this was mostly some lazy gradient evaluations, where you simply not compute all gradients, but just a few ones, well, a single one, and you keep all the other ones from your memory. But you also can give some variance reduction, where the idea is that you take the stochastic gradient, which is unbiased in the sense that the expectation over your own randomization is a full gradient of the whole cost function, but you get a large bias. And this large bias prevents you from having fast convergence. And those techniques can be seen as trying to reduce the variance. And this has allowed a lot of extensions. And one of them being important is SVRG where you are able to avoid storage. Okay, so I don't want to spend too much detail, but if the storage of gradient is an issue, SVRG is a very nice way to avoid that storage. All right, you can also do acceleration. Okay, so this has been done not by my group, but by many different people. So this is the new way to replace n plus condition number by n plus square root of n condition number. Okay, and this has been done in special cases by Shai, Schwarz, and Zheng, Nintenda, Land, Efazio, so Alan Zhu. Also very nice generic work by Lin, Meral, and Arshawi, which is a way to accelerate any non-accelerated techniques. So here, I think I'll come back to that later, but at the end now, with that rate, you are optimal. Okay, in the sense that if you want to minimize the finite sum with smooth components, which is globally strongly convex, you cannot do better than this. Okay, so now we have reached the situation where we have both an upper bound like this and a lower bound. All right, so now to finish on, maybe I can take like a few questions, maybe 2 or 3 now, because on the variance reduced techniques, because I'm going to change a bit gears after.
Yes. So Mrinank asked that, how are we fixing the learning rates to make this comparison? Perhaps with a larger batch size, we can use a larger learning rate because the gradient is less noisy.
Oh, okay. So here I think this is, as far as I remember, this is plain SGD, so a mini batch of size 1, and we tried several step sizes, and we would select the best one. If we had some mini batch, then indeed we could do a bigger gradient step. Okay, but then the x-axis will be modified because you do fewer steps because of the mini batches. When you see, if you take mini batch of size 10. Once you see the whole data set, you have done 10 times fewer updates. So typically, from what I understand, is that mini batching is not helpful in terms of pure iteration counts or convergence bounds. To me, the gains, in fact, you can show it's a bit worse, but the gains are really in terms of block access data. But this is my own take, but I'm willing to be challenged on this one.
So the other question by Maximilian, did you compare to adaptive SGD algorithms like Adam? Probably Adam was not even there, I don't know.
At the time, Adam was not even there, but on those ones, I think people have done it, but it's Adam will be like among the stochastic gradient ones, maybe a bit below, but Adam suffers from the same, benefit from the same and suffer from the same conditions as SGD, meaning that it does optimize test error, as I will mention in a moment, but also it cannot get to like exponential convergence. It's a good way of reconditioning, okay, like adaptive methods are reconditioning. So you may improve on the condition number, so we'll go a bit faster, but this will not like change much.
By Robert, what is the complexity for accelerated methods in the strongly convex case?
What is
the complexity for accelerated methods
for I think this is here. Okay, this is complexity for the accelerated method. So this is just so this is on the slide. I don't get the question in fact.
So Kumar Chitij asks, do some or most of these methods match the lower bound in terms of condition number?
I think the lower bound is matched by the accelerated version. And this is what to expect, because in the non-stochastic case, the lower bound is matched by accelerated gradient descent. And so you want to make sure that if you have a single function, you go back to the deterministic case and you need to use acceleration. So you need acceleration to match the lower bound. And this is what is achieved by those people. Okay.
So there are 2 more questions. Do you want to take it now or later?
Maybe later. I want to make sure I get to the end of it.
Yeah. Okay. Perfect.
All right. So now let's look at the testing costs. Okay. So I think this is something which is often overlooked by my colleagues from optimization, not so much for machine learning, but it's important to make this very clear. is that now the goal in the next few slides will be to minimize a function f, which is the expectation over some distribution P of xy of some loss, exactly the same. We don't have any more observations, okay? It's not an empirical average, it's just an expectation. And of course, we need to have access to f in some way. So we cannot access the expectation. We access f through samples, okay? And samples are independent. So we have a stream of samples. Every time you can ask for a new sample, xi, yi, which is independent, very important. And if you do a single pass, okay, over the data, and why a single pass? Because you need those samples to be independent. So if you see data point a second time, then the samples become dependent, and the bounds that I'm presenting are not valid anymore. And then if you do this, all the AGD, classical AGD error bounds applies to this function f. Okay, and f is what? F is a test loss, okay? It's a test error, test risk. So this means that what I was doing before, so the expectation now is with respect to the data, because every observation is random, and this is the excess risk between the test performance of my estimator minus the best test error in my class. Okay? And so what we have seen is that the rates of 1 over root n and 1 over mu, okay, that we have seen yesterday are now optimal. Okay, so this is also from the work of Nemirovsky and Yudin, and those bounds are generalization bounds. Okay, this is bounds on unseen data, so you should not expect exponential convergence on unseen data unless you assume some very strong assumptions. And it turns out this is achieved by AGD. Okay, so those slow rates of AGD on the training error is a bit unfair because you can also get good test error. And so in that setup, there are people have considered, and in practice, people do a lot, constant step size AGD. Okay, as I've mentioned before, because of the noise in the gradients, this will not converge. And the question is, can you make it converge? And do you get robustness to real condition? Okay, so this is the first thing, the joint work with Eric Bolin from a few years ago, and this is for least squares. So for least squares, it turns out that the fact that you oscillate around the optimum, okay, is not a big problem because since the gradient is a linear function, you can essentially invert the operations, swap the operations of gradient and expectations, and at the end, the average AGD will converge. Okay, so before averaging, you will not converge, you will oscillate around the optimum, but after averaging, you do get something which is converging. Okay, and what you can show is that now the convergence rate is 1 over n without any mu. Okay, so this may look like a minor thing, but remember that mu can be very small, and when I say small, it can be 10 to the minus 12. So relying on strong convexity on the testing data for the testing distribution is hoping for a mu which is very small. Okay? And so if you make mu disappear, this makes a strong difference in theory and in practice. And here I'm just showing on a simple example something like this. We have a constant step size with a decaying step size. Okay, it's a bit slow, but with a constant step size, you get quickly to the solution. And just to give you some insight, I think it's important, and this has led to quite a few extensions. In that is to understand what the iterates of AGD are. So this is like the squares. Okay, so the square laws. This is my prediction function, which is a dot product. This is the gradient of my loss, okay, over there. This is my recursion. And the way we see AGD, like in a theoretical analysis, is through the Markov chain. Why? Because given theta n minus 1, we add some new randomness, which is independent from the past. This is where a single path is important. So you add new randomness. So the theta n minus 1, the theta n forms the Markov chain. And the beauty when you have a constant step size is that the Markov chain is homogeneous. The dynamic is the same throughout the iterations. If gamma was depending on n, then you would change the dynamics at every time step. So it's not homogeneous. And the good thing with homogeneous distributions is that typically Okay, of course, with some added assumptions, then they converge to some stationary distribution. Okay, so wherever you start from, the theta 0, you're going to converge to a distribution which is always the same. Okay, you call it pi of gamma, and so you'd end up always oscillating around some value, which is the expectation under that stationary distribution, which is written over there, and you oscillate over it. So this is true for all problems in LGD. You start somewhere, you lose where you start from, you end up oscillating, okay, and you hope two things. You hope that you lose the initial conditions as fast as possible to get to the vicinity of the end, and you hope that those oscillations are not too big, or you oscillate around something good. It turns out that for least squares, you oscillate exactly around the good things. Okay, and so if you do averaging, then you're going to converge to the global optimum. And this is classical in Markov chain theory. Whenever you average something over the path of the Markov chain, you converge to the expectation under the stationary distribution. So theta bar n should converge to theta bar gamma, which happens to be theta star. Okay, so this is the reason why constant step size LGD is working for least squares. Okay, so I've mentioned least squares yesterday as a good way to get bounds quickly. So here, least squares is a good way to get like LGD with a constant step size to converge. And here, the constant gamma is big. Okay, the idea here is to take gamma as big as possible as long as you don't diverge. Okay, it's not like a small step size, it's a quite big step size. And the big step size will allow you to leave theta 0 very quickly. Okay, it's going to be like exponentially convergent at the beginning, and then the oscillations will be reduced by average. So this is what I've written over there. Okay, so just to highlight this on a very small data, dimension 20. Okay, so this is number of iterations in logarithmic scale, distance to optimum in logarithmic scale, before averaging in dotted, and after averaging in plane. And if you look at various constants in the step size, okay, so if you do constant step size, you don't converge. Okay, so you oscillate, there's no convergence. As you lower the step size, you get a bit lower, you get closer and closer. It's normal. Smaller step size mean smaller oscillations, but you don't converge. But as soon as you do averaging, you get to a very nice line, and the slope of the line you can check is -1. Just to highlight the fact that constant LGD is not converging. Okay, so it's always oscillating. All right, so that's some benchmarks. Let me go through. So you may say, who cares about least squares? Okay, so when least squares is just a way to analyze something in an easier way, and your algorithm is still working beyond least squares, it's fine. But here I'm leveraging least squares to make the algorithm work. So is it possible to make it work beyond least squares? And there is a way, which I will not describe too much in detail, but there's a very simple way to make it convergent. Okay, and the simple way is to do some form of Newton step, because I don't want to spend too much time there, but the idea is that when you solve a Newton step, as I've mentioned yesterday, you are solving a quadratic approximation. Okay, so since we know that constant step size LGD is working well for quadratic functions, it's somewhat natural that if you approximate your problem by a quadratic function, you can run a constant step size LGD. So here, the nice aspect over there is that you never need to form the Hessian. So you preserve the O of n, O of d iteration cost, and you preserve the convergence rate. So if you want to know more, you can look at the paper with Eric. All right, so a big important question, which I will not cover in this talk. You can look at a recent paper by Lucas, Pio Vivian, and Alessandro Rudi, is what we'll do in practice. So in practice, okay, people do multiple passes. So here, to get the good test error, I told you, oh, do a single pass. So the question is, who's correct? The practitioners that all do multiple passes, or the theoreticians that always say do a single pass? And my answer will be they are both correct and incorrect. And if you want to know why, you can look at the paper, and where we show that for simple problems, a single pass is enough, and for hard problems, you need multiple passes. And we we characterize the amount, what it means to be hard or easy. So if you want to know more, there's a recent paper about that. All right, so a few perspectives on stochastic gradients. So I think here what I presented like a bit yesterday and today is a sequence of provable and precise rates for stochastic gradient and for the linearly convergent extension. So I insist on the precise rate, very important. Having exponential convergence, but with a rate which you don't control, to me is not very meaningful, because if that condition number is 10 to the 12, oh, sure, it's linearly convergent, you're going to see it only after 10 to the 12 iteration. It's really important to, if possible, of course, to be able to put, to give a number, okay, a number which you can control. And here, the number here is controlled by condition number. Then it does improve on two lower bounds, okay, of course, by leveraging structure. And I've not presented the extensions, but there's a whole zoo of extensions, okay, of various reduced techniques. You can do proximal steps. So I've mentioned the L1 norm yesterday. If you add some L1 penalty or some like constraint, if you add projections, then these convergence rates are preserved. If you want to do saddle point problem, you can do similar things. And pretty much whenever your algorithm has an iteration some finite sum, okay, then you can leverage variance reduction or lazy evaluations. And then, of course, there is no general proof for all of those, but you can often apply the technique, which comes for free, just try it. And you can prove it typically reasonably well. I would like to mention the interpretations. Okay, so variance reduction is very important because it's a simple way to extend to new techniques. And I've not mentioned the proof, but the proof for SAG is a bit involved, whereas the proof for variance reduction is much simpler. This is one example that you have an algorithm which is fast, but whose understanding and proof are a bit mysterious. And then by having a better interpretation, first the proof is now like half a page, okay, a dense half page, but still a half page. And then this allows for more for easier extensions. So extensions, so I think lower bound for finite sum, I think this is now achieved by LAN. Okay, so if you use acceleration, then you get lower bound. So now the problem is more or less solved. I say more or less because it's not because you have a lower bound that things are over. Okay, there's still some progress, but you should not expect improving the rate so much. Very nice size of work by Gorbus Balaban, trying to go to look at sampling without replacement, which tends to make more sense because when you sample with replacement, some data points will almost never be selected. Okay, it's a classical problem in probability, and sampling without replacement makes more sense because you make sure you see data points more often. And if you do sampling without replacement in all of those techniques, it tends to work like similarly, and it's a bit more stable. Of course, like trying to get bounds on testing errors, this is very important because at the moment we get mostly bound on the training error. Okay, we like to leverage also those techniques to get provable bound on testing errors. There are already a few works about this. And then like more open, how do you do like parallel techniques? Okay, so let's say you have several computers or several cores. And the idea is that you want to distribute the fast techniques. Okay, so what is often done when you look at parallel processing is that you take like HGD with a decaying step size, so it's very, very slow. And then very slow is also very robust. And then you put it on several machines, and you say, oh, look, I make the algorithms like m times faster with m machines. The only issue is that you've chosen one of the slowest possible algorithms on a single machine. Okay, if you like decaying step size HGD, at least for those problems. Now the question is, can you distribute the fast techniques, okay, and obtain linear speedups in the number of machines? And there's nice work by Rémi Leblond, Pedregosa, by Fabien Pedregosa, and Simon Lacoste-Julien. And also, we have some recent work with Adrien Hendricks and Massouillet showing that it is possible. Of course, there's still a lot to be done there because it's still like still not perfect. that you can parallelize those techniques and benefit from the fast techniques, even if you have multiple computers. Big open problem as well is non-convex problems. There's a size of work. So Reddy et al. Is one of them. There are also, of course, many other ones. And the idea, can you also leverage bias reduction in non-convex problems? So here, I think this was mentioned during the Q&A session yesterday, is that it's you can do it on the training set. So this works on the training data set, but how it extends the testing error is a bit unclear. Also, other forms of acceleration. Okay, so here I've mentioned several times Nesterov acceleration, and there are other ways of doing it, in particular Anderson acceleration. You can look at that paper. And finally, I think I've mentioned it already several times, is anything you can do to make the problem better condition. Okay, so by adaptive techniques, which are rescaling method gradients, or quasi-Newton is always welcome. And before I move on to the last part, maybe I can take a few more questions.
Yes. So in Q&A, there is a question: what additional assumptions could be useful for ML losses that can be beneficial from an optimization viewpoint in the future?
In the future, I don't know, but in the past, I know. Okay, so one of them is what we call a self-concordance. Okay, so this is a property of the third order derivative to be bounded by the second order derivative. So this has been used by Nesterov and Nemirovsky in a different form. Okay, you have a power 3/3 appearing. It's a way to show global convergence of Newton method. And so why is it important to use those techniques? Because you can leverage the proximity with quadratic problems. Okay, so several times today and yesterday, I've mentioned quadratic problems as being important to study. And when you want to see how you can relate to a quadratic problem, okay, you need to know more than simply like bounded Hessians. So you need to know a bit more. So bounded third order derivative is a bit too much. Okay, and one way to do it is by bounding the third order one by the second order one, and this happens to be true for logistic. So this is why I think it's important. You also have an X concavity, which is a classical assumption. So this is for the assumptions like beyond convexity, which have been used in the past, and in the future, I wish I knew, but I don't know.
Other question is, can you please comment on how to do line search for stochastic algorithms? Do you consider every function in search?
Yeah, okay, so this is to me still a hard problem, okay, and the way line search is working is a deterministic setup is by trying several values, okay, computing the cost function at that value and hoping ensuring some minimal progress. The issue when you're stochastic is that you cannot compute the function values because you only have access to stochastic functions or stochastic gradients. So now you have to estimate the progress in some kind. And at the moment, what I know works well is simply to have some validation sets. And when the error of the validation set does not go down anymore so much, you lower the step size. Okay, so this is very pragmatic. I think by now there are some analysis of this, but doing something like more subtle is difficult. The difficulty is that if you start to lower the step size too early, you slow down a lot. Okay, and so it's hard to detect when you should decrease the step size, but I think it's still an active area of research. And one good thing about those variance reduced techniques, at least for convex problems, is that the need for adaptive step sizes is not as strong because the method is already reasonably well. Also, if you take like constant step sizes, okay, also it matters a bit less because what is killing you when you have a decaying step size is that you have to start big at the beginning, okay, and because of the reduction and of the step size by 1/√t, and so this makes it a bit more harder to tune. But with the constant step size, it's a bit easier. But this is still like a somewhat open.
So there are two more questions, depending on if you want to take it in there.
Go ahead.
So if one wants to choose If one wants to lose or forget the initial state as fast as possible, how does that fit with the idea of learning rate warm-up?
Learning rate what? Warm-up?
Yeah.
What is, I don't know what learning rate warm-up is.
Oh, I don't know either. So let's move on to the next question. Probably you can ask in the roundtable.
Yeah.
Is there any work trying to combine the fact that we are minimizing the sum of n function and the fact that the optimization problem is separable, i.e. work trying to combine SGD and coordinate descent?
That's no, you could. In fact. So what you can do, and this is like a nice area of work, is if you take the min-max formulation. Okay, so if you take the min-max formulation, then typically you get a min-max and you get a bilinear form where your data matrix appears as a theta transpose data matrix transpose a dual variable. And now you can do AGD on the whole matrix. Okay, so you can AGD, typically we select like lines of the design matrix. Convergent, we select like columns of the design matrix, and then you can select arbitrary blocks or numbers. Okay, so this is one way to do a bit in between the two. And you can combine the two also by being both stochastic. You choose a function at random, and on that function, you select only a coordinate. But then you have to be careful that it only makes sense to have like simpler iterations if they are really simpler. Okay, so you want to avoid. So I don't know how you can select a point, do some coordinate descent step, which is like d times slower than doing the full step. It may be possible in some setups, but it doesn't seem obvious to me to achieve this like in all cases.
There are two more questions.
I think I'd like to move on, and then we can to make sure I have time, and we can ask.
Yeah, sure.
Okay. All right, so now let's try to go beyond convex problems, because I think, as I've mentioned, this is like still a lot of problems over there. So now I will talk about like a recent line of work that I've worked on with Lénaïque Chizat, trying to provide some global convergence guarantees for those problems. Okay, so as you will see, this part will lead to a lot of open problems. Okay, and this is where I will mention the interaction between hype and learning theory. All right, so this is like a review slide. I have my observations, my prediction functions. I have my empirical risk, okay, and this is a training cost as a test error, okay, the usual thing. And as I've mentioned, this problem is convex. The loss is always convex in my case, and the problem is convex when H is a linear function. Okay, so it's convex loss and linear predictions. So what I've tried to present, like in the previous slide, is that for those problems, there is some approximately matching theory in practice. So of course, the bounds are just upper bounds. So don't get me wrong, the bounds are very loose, but their behavior is a good predictor of empirical performance. And whenever you have some improvement in theory, then you get some improvement in practice. And one example is like non-uniform sampling. So it's sometimes hard to. So if you want to do non-uniform sampling, you can cook up or cook out, I don't know, heuristics. But if you use the bound to do it, it's very efficient. If you mix with acceleration, it's impossible not to use a theory to set up those non-uniform sampling and those like momentum terms. So it's a case where the analysis is both quantitative and does suggest improvements. Okay, and I remember from one of my papers on variance reduction, before non-uniform sampling, it was not working at all. It was slower than gradient descent. This was for min-max. This was for min-max problems. And as soon as we did the math to derive the proper non-uniform sampling, it started to work much better. Okay, as you can see that sometimes the theory will help you design just a better algorithm. And this like nice state of affairs has been like leading to what I call the golden years of convexity in machine learning. So starting around 95 and were SVMs. And there's a lot of areas. And if I'm missing any, I'm sorry, and I should add it, but my slide is a finite slide. So we had like sparsity a lot for a while, a lot of convex relaxations. I think you had the optimal transport lecture this morning by Marco Couturier, and I presented like HGD, like in many cases. And so I made it stop in 2020, because I don't know what's going to happen next year. But of course, there's still a lot of opportunities for convex problems. But really, in those years, you had this exchange between theory and practice, which was really strong. And so for HGD, okay, which I've presented, this is like this exponentially convergent finite sum. So this was a SAG, SDC, and so on. So here it's just a review of what I've just presented. You follow the gradient, okay, plus you add those terms to make some variance reduction. And at the end, you get some very nice convergence results. You can accelerate. Let me skip this. And let me just skip this. Then you have important matching lower bounds. Okay, so this is something also which I like in that like convex world, is that some people try to work on algorithms. Okay, some people try to work on guarantees for those algorithms, and some other people are trying to show what is the best you can, the best you can hope for. Okay, and once everybody is agreeing, then this is nice, because you get to a problem where you know what's happening. I think this is very nice. And as I've shown like earlier today, so this was my wishful thinking slide, and that wishful thinking slide is not so far away from what you see in practice. Okay, so this is me drawing, and this is Mark and Nicolas coding, and you end up with things which are a bit similar. Okay, so the matching is not perfect, of course, but I think you get some nice behavior. And as I've mentioned earlier, the analysis does suggest some improvements. Okay, so non-uniform sampling. So what I've showed like in the first part of today's lecture were examples where before non-uniform sampling was not working very well, and after it was really working much better. And those were given by theory. You could have imagined to find the hack to do it, but I think the good thing is that this was given by theory. In acceleration, I think, so the momentum term, if you do that plain HGD, okay, you can fiddle with it and find a reasonable value. But if you start to do acceleration plus variance reduction, those methods tend to be unstable if you don't have the proper tuning. Okay, and this tuning is being given by the theory, and this works very well. And finally, you have matching upper and lower bounds. I think it's very interesting. Okay, so the two aspects. Okay, and there are many other areas. Okay, again, you have, if you do sparsity, you can do it. If you do non-parametric, you can do it. All these randomized linear algebra, you can do it. If you do bandits, you can do it like similarly. So there are many other areas where typically there is some convexity hidden in the background, where you have a good exchange between theory and practice. Okay, so this was like all very good, but now there's a new player in town, which is deep learning. So does this apply to deep learning? There's this nice exchange between theory and practice in the two directions. And we'll see that we are still far away, and this will be like still lots of open problems. So let me present one recent progress, trying to look at this. All right, so this is the a deep network, okay, with 3 layers, but 2 hidden layers. And again, you start with some linear function, you apply some nonlinearity, and go on, linear function and nonlinearity. And yeah, this is what you have. So first, this is a strong simplification. Okay, so in practice, for computer vision, NLP, and so on, this is much more complicated now. You have some pooling, you have some convolutions, you have like whatever gizmo they invent every week, but it's much more complicated. Okay, so I'm going to focus on the simplest problem, fully connected networks, and as you will see in a moment, it will be even simpler, a single hidden layer. So there are 2 difficulties with those problems. Okay, first, this is a non-convex optimization problem. Okay, because you have some nonlinearity over there, and this will be the focus of this part of the lecture, because this is like a lecture on optimization. But also, another difficulty is the fact that typically in modern deep learning, the number of neurons starts to be very large. We often call that the over-parameterized regime, where the number of parameters is far bigger than the number of observations. So typically, you can get a perfect fit. Okay? And although you get a perfect fit with zero loss, this is still generalizing, and it's very nice. There's a lot of work on trying to understand this. You may have heard of double descent, of things like that, and of implicit regularization of AGD. So those are aspects which are interesting, but not the topic of this work. You can ask me questions if you want at the round table. Okay, I will mostly cover the first part. Okay, so in terms of optimization, what can go wrong with non-convex? Everything can go wrong. Okay, so first, you may have some local minima. So it's a function in 2D. Okay, with so this is the global minimum, local optima, global maximum, like saddle points, and so on. So you can typically gradient descent will get stuck in any stationary point. This can be this one, this one, this one, this one. It can be also the stationary point over there, saddle point. So this is like everything can go wrong with non-convex, and you need to be careful in terms of points where you converge. In the convex case, you wouldn't care so much because unless you're super stupid, you always converge to the global optimum. So first, okay, so what people have been trying to do, and I've mentioned it yesterday, is to provide local guarantees. So you replace distance to optimum in terms of function values or distance to optimum in the L2 norm by a norm of the gradient. Okay, so you show that the norm of the gradient for your iterate or at least one of the norms of the gradients along your trajectory is going to 0 at a rate which is typically the same as for convex problems. So of course, you cannot use strong convexity there, but typically the rates for non-convex end up translating more or less to the convex world by replacing the criterion for optimality, which is not global optimality anymore, but simply like a norm of the gradient. So that's a nice size of work by Lee et al. And Jean and colleagues and many others. But this is only local, okay? So you may end up being there instead of there. Okay, so this is not providing any formal guarantees for deep learning. Then you may think, why can't we get global guarantees? Okay, so I don't know if you have some lecture on Bayesian optimization. Okay, but if you do, I ask you to show this function to the lecturer. Okay, because this is a function showing that it's hopeless to obtain some form of global guarantee for optimization. So if you have a method that can take any function and get you a global optimum after some number of steps, that number of steps has to be exponential in dimension. Why? Because if I give you this function, which is like flat everywhere except in a small area, and that I'm going from 1D to multiple dimensions, the volume of the area where things are happening is going to 0 exponentially fast in dimension. And so unless you end up there by chance, you can never find it. Okay, so this is a classical lower bound for smooth optimization. So it's hopeless to hope for a global guarantee. Okay, so whenever you see algorithms claiming to optimize functions with no assumptions, then it has to be in low dimensions, or of course they end up in a local optimum. But then you would say that who cares about those functions? Okay, it's not very interesting. Okay, so when you optimize neural networks, you hope you're not in that area. Okay, so let's try to look at functions that we care about. And this has been done by several setups, for example, by a team at NYU, led by Anna Choromanska. So what they've shown is that they have exhibited a class of functions, okay, for which they were non-convex. So you had like stationary points of many kinds. You had like local minima. You had like saddle points where the Hessians had both positive and negative eigenvalues. So one example over there. So this is a point where you have directions of descent over there and direction of ascent over there. And in high dimensions, you count the number of negative and positive eigenvalues. And what they have shown is that there's a class of functions, okay, for which all local minima happens to be at the same energy level, the same function level as the global optimum. Okay, so meaning that whenever you end up in the local minimum, regardless of which one you choose, is pretty much the same performance. Okay, so this highlights the need to to escape stationary points which are not local minimum. But the issue is that their class of function is a random class of function, but the link with neural networks is a bit far because they need to add a lot of independent statements which are not valid in practice. Another interesting line of work is by Soltanol, Kotabi et al., where they show that for some activations, like quadratic activations, like you replace the Roux by the square function, then your problem does not have bad local minima, in the sense that every local optimum is a global optimum. And hence, if you can avoid stationary point, again, you're doing well. But the issue is that it's only applying to activations which people don't use in practice because they don't benefit from the non-parametric aspect of neural networks. All right, so let's try to look at what can be shown. So I'm going to select to go to the simplest possible problem, which is a single hidden layer. So input layer theta 1, okay, output layer theta 2. Okay, so you can write down the prediction function as a sum over whole hidden neurons J over there. So you have 4 neurons of the output weight, a single weight, because I'm assuming a single output, a real valid output, times the activation function, think of a Roux or a sigmoid, of the dot product between your input vector and your input weights. Okay, so this is a classical neural network. And what's key here is that and this is the reason why we only focus on one hidden layer neural networks, is that you get a sum, okay, of different prediction functions. Each of them has its own parameters. Okay, there is no sharing of parameters between two different J's. Okay, so take that hidden neurons. It has parameters, the input weight and the output weight. These ones are also parameters, but there's no sharing of parameters. So at the end, you get formally something of that kind where your prediction function is a sum, okay, over own predictors with no sharing of parameters. Okay, so this is really important for the analysis, and this is why we cannot go to more than 2 layers, because as soon as you get one more layer, you start to have sharing of parameters. And in fact, this is one reason why you do neural networks, is to share parameters. Okay, and so this is not possible in our analysis. This is why we stay only to one hidden layer. Okay, so I'm calling WJ that set of parameters associated with neuron number J. Okay, and my goal is still to minimize some empirical risk or expected risk, okay, which I'm assuming to be convex in the prediction function. Again, I've mentioned it yesterday. This is a weak assumption. We are only we assume a logistic loss or square loss. So it's not the difficult part is the fact that psi of W is not linear in W. Okay, you have some nonlinearity over there. Okay, so the main insight that we're going to look at, and this is not our insight, this has been used for quite a while in statistics and signal processing, is to realize that when you have a large finite sum, which is independently parameterized for each component, you can see it at the expectation, okay, of the function psi of W, okay, with respect to some empirical measure composed as a weighted sum of Diracs. And the idea is that if you go over parameterized, so you get more and more Diracs, at the end, you get more and more Diracs, so you will converge hopefully to some distribution with some density. Okay, so the idea, as you get more and more, you end up being more or less of that form, and you can hopefully analyze problems where you have a density like this, and this should give you insights on what's happening with a finite number of neurons, finite and large number of neurons. Okay, so this is really the insight that we're going to look at. And it's one way of seeing it is we are linearizing the problem. Okay, this is non-linear in WJ. We change the point of view, okay, see through a measure mu, and now this is linear in U. Yes, we have made the problem linear, and we have found a parameterization where the problem becomes, the prediction function becomes linear. As I've mentioned, this is not new. Okay, this dates back from Barn in the 90s, and this has been looked at both in statistics and signal processing, and by also like Nicolas Leroux and Joshua Benjo and colleagues, and by myself a few years ago. It's really like a classical idea, and often it's called the mean field limit in physics. So often the W here I've seen as particles, okay? And if you have many particles, they have some global behavior, and that global behavior is characterized by the density. Okay, so this is very common in physics as well. All right, so now that I've made the problem convex by linearizing my prediction functions, maybe it's over. Okay, why? Because R is convex. This is a linear function, so I have a convex optimization problem. Okay, so I love convexity, so it should be fine. We have lots of algorithms. The issue here is the fact that the set on which I am optimizing, the set of measures, is infinite dimensional. Okay, it's a big object, so it's not going to be easy. But then I can look at my friends from optimization. We know how to optimize over big sets. Okay, in particular, if you have the convex hull of a lot of elements, and probability measures happens to be the convex hull of all Diracs, essentially, then we know how to optimize over convex hulls. Okay, this is what Frank Wolf techniques are for. Okay, so I don't want to spend too much time on that. But those techniques are simply a way to add Diracs one after the other. Okay, so this is a way to express a point in a big convex hull as the convex combination of only a few points. And those few points are being incrementally added to the problem. And this is often called incremental learning. So this is all nice because you get a nice convergence rate, like 1/k after k iterations. But the problem is that the task of adding a new neuron, okay, happens to be NP-hard. Okay, so you replace a non-convex problem by a sequence of NP-hard problems. So it does not help much in terms of theoretical guarantees. And even worse, nobody will use that in practice. Okay, so what people use in practice, this is just like backprop, which is gradient descent on the particles. Okay, so here again the W1 here are the parameters associated with the first hidden neuron. So you do gradient descent. Now you have three questions. So if you want to combine this insight of going to the infinite number of neurons, of hidden neurons, you have three questions. Will the classical algorithm converge to something when n goes to infinity? Does it converge? And does it do very well? Does it predict well? Okay, so I'm not going to cover the prediction performance. So we have a paper at Colt this weekend. I don't know when Colt is, but soon. I think this is this weekend, next weekend. I don't know. It's very soon. So you can have a look at this. I'm going to focus on the first 2 points. So we consider this general framework, which is motivated by neural networks. Okay, but this goes beyond neural networks. Whenever you want to learn, you have some convex loss over some finite number of prediction functions, then and you want to optimize with gradient descent over the W's. So again, this is not convex in Wj, okay, because of the psi. So what I'm going to do, and this is like another simplification after many of them, I'm going to look at the gradient flow. So the gradient flow is not anymore gradient descent, which is a discrete time algorithm. I'm looking at the continuous time algorithm where I'm really following the steepest descent direction on my space of weights. Okay, so why are we doing this? First, to make our life easier. Okay, and of course, this is not totally useless, because you can often relate the gradient flow to gradient descent in various ways. If you do a single pass AGD on the expected risk, and then you can show that this, where the step size goes to 0, you're going to follow the gradient flow. Okay, so this shows that if you know something about the gradient flow, it is likely that you're going to say something about the SGD on the test risk in a single pass. So of course, this has to be proven. Okay, so we have not done it. This is simply like, if you cannot do the gradient flow, it's unlikely that you can do the SGD. And again, if you have the empirical risk, if you do any form of gradient descent, will also, when the step size goes to 0, converge to the gradient flow. Okay, so you can see the gradient flow at the limit when the step size goes to 0. So first question, what do we tend to when m goes to infinity, m being the number of neurons, or what we call often the number of particles. First, it has a name. It's called a Wasserstein gradient flow. So this relates to the optimal transport talk of Markov, but probably Markov will not talk about Wasserstein gradient flow. It's a bit too advanced for now. But the idea is that you move along the steepest descent direction. So you look locally, okay, where you go as low as possible, but you look in the neighborhood in terms of the Wasserstein distance that you have seen probably this morning. And this happens to be exactly the limit when m goes to infinity. So it is important to have a limit, mostly to make sure that this is well defined. Okay, so often when you go to get more and more particles, you want to make sure that this converges to a well-defined object. Okay, because sometimes it may totally be diverging. This is converging, and this has a name. And if you want to know more, there's the size of papers, and this started by Nitanae Suzuki in 2017. I've worked on it with Nick Chizat, and there's a lot of people leveraging this convergence to this Wasserstein gradient flow. What I want to focus on is this limit. Okay, so now we have convergence. We know that when m goes to infinity, this does converge to some object, but that object, which is a gradient flow, does it converge to the global optimum? And the result that we have is that it does converge to the global optimum. And here I've put informal theorem because there are assumptions. Okay, there are some technical assumptions. It is very different from what I've showed in the yesterday and in the first part of the lecture. In the first part of the lecture, there was nothing hidden. There were no technical assumptions. All of them were given. Convexity, smoothness, or strong convexity is like very, very precise, but nothing hidden. Okay, no like, oh, it has to be like some weird like technical assumption with a name that you don't know. Okay, and so here we have a few of those because we have only, this is common with the qualitative statements. Okay, often you need some like topological assumption about the compactness of some sets and so on. And so if you're in that type of mathematics, you can have a look at the paper. And here I want to focus on the what needs to be true for this to be valid. So we need like two key ingredients because, of course, it is not true that when you launch any gradient flow, it's converging to the global optimum. And the two ingredients are homogeneity and good initialization. And the first homogeneity, this is where neural networks come handy. We need our function C of W to be at least homogeneous with respect to some of its parameters. So for a neural network, you're always homogeneous with respect to θ2. So homogeneous means that if you multiply a parameter by lambda, you multiply the output by lambda as well for positive lambda. So this is homogeneous with respect to θ2. And if you have the Roux, which is the max function, the max of your argument and zero, you're in fact fully homogeneous with respect to the entire function. So if you multiply the input by lambda, you multiply the output by lambda squared. So this is really important. This is why it works, and this indicates that the Roux, which is like really homogeneous, helps a bit for optimization. And then the second condition is that you have to start with initial neurons which are well spread. Okay, meaning that you have to cover all directions, and the way to cover all directions is to sample from uniform set of directions like from Gaussian. Okay, this is essentially what people do in practice. When you initialize neural networks, you initialize with random Gaussians, and this is also what we need to get this result to be true. So let's see how it works. First, before seeing some simulations, it's only qualitative. Okay, so in the sense that I will not tell you, oh, I need that many neurons for this to be true. I need that amount of time for this to be true. I wish I could do that, but it is still an open problem to have any quantitative statements. So let's look at some super small problem, dimension 5. Okay, so I'm generating data from this from a neural network with 5 neurons in dimension 2. Okay, I'm running like a AGD on the single pass AGD on this cost function, and I'm plotting the neurons that I obtain. So in dotted, this is generating neurons, and the particles here in red and blue, this is what I'm learning. Okay, so I can launch the optimization with various number of neurons, 5 like the generating network, 10 or 100. So as soon as you are more than 5 neurons, because data were generated without noise from 5 neurons only, there is potential to converge to the global optimum, which is 0 loss. Okay? And as you can see, with 5 neurons, we could convert to 0 noise, to 0 loss, but we don't achieve we don't find the good neurons. Okay, so this just highlight that there are local minima, and you get trapped into it with only 5 neurons. What our results suggests is that if you have lots of neurons like this, then they should all converge. You should end up converging to the global optima, which is those 5 neurons. And this is what you observe, okay, that they all start like from a small ball around 0, which is like uniform distribution, and they move away, and I'll show a video in a moment, to the correct neurons. What is surprising and still unexplained is that even when you start from 10 neurons, only twice the number of neurons that you need to achieve the global optimum, then you also converge to the true neurons. Okay, so this is like something which is still not explained. I have some video of the upper right corner. As you can see, you start from this, and things move in quite like funky way, and they end up converging. So if I start again, you see that they leave and they end up in the same place, always along the correct neurons. So it's just to highlight the fact, it's just to illustrate the result from the previous slide. If you over-parameterize, then neurons will tend to converge the correct ones. So this applies to other setups like spike deconvolution. So if you know what this is, this also applies exactly to this. All right, so this was only qualitative. Okay, so can we make this quantitative? Because I think the field of learning and optimization have strived with like quantitative results. Can we do it? So I think one good attempt by May, Montanari, and Nguyen is to add some noise, okay, in the dynamics, and then you can prove many things. In particular, you can be quantitative in the number of neurons. But the issue is because you have regularize the problem, you don't converge to the global optimum. Okay, so this is like very good attempt, but it's still not there yet. And then when we were struggling with Lenaik, Chizat on trying to find good results, we saw like a burst of activity on archive. So this was typical from computer vision. Okay, this is like the regular world of vision and NLP, but there was like 5 papers at the same time doing all like impressive things, okay, claiming they had solved the problem and so on. And for example, they had like results like global quantitative convergence of random descent for neural networks. This was working for deep architecture and skip connections. Okay, for us, we were not able to go beyond like one hidden layer, and they were doing everything. Okay, so what is the link between the two? Okay, and let me try to express what the link is. Okay, so what we have done, what I've just presented, this is the so-called mean field limit. So I get an average. My function is an average of predictions. And if I initialize randomly and the number of neurons goes to infinity, I'm converging to the minimizer of this thing. Okay, so this is what I've shown. And what those papers were doing were essentially doing the exact same thing, exact same algorithm, but multiplying the input weights, initializing square root of m times larger. Okay, so when m goes to infinity, then this will be very large. So they did add some scaling behavior, which turned out to be quite important. Okay, so what we have shown with Enaik and then with also Edouard Oyalon is that this does converge to indeed the results are true. Okay, of course, but we show that extending results from Jaco and colleagues that the scaling behavior is very important, and just to highlight the fact that a small change, okay, can make a big difference. So let me explain for the next like 5 minutes what we call lazy training, because I think it's a good example of optimization doing something which looks good in theory, but which is like not what you want to do in practice. All right, so this is a bit, this works for any problem where you have some loss R and some prediction function H of W. Okay, you can think of H as being a set of neurons like this, like I've presented, but this works for everything. Okay, so the way those techniques are working by replacing the cost function by adding a scale factor to the prediction function, which is very big. This is going to going to infinity. So of course, if you take your favorite prediction function and send it to infinity, this is going to be totally useless. Why? Because you're going to be like in very weird part of the loss function. So this will not do anything correct. But, and this is very smart, if your initializer, when you start the descent, each is such that h is very small, close to 0, then you're not going to send it to infinity. You're going to stay where you are. In particular, if you start for almost 0, okay, then you can send it to infinity, but infinity times 0, you have a hope for having some interesting behavior. And it turns out when you do initialize randomly, okay, typically, and this is true with for neural networks, because you have like output weights which are normal, like Gaussian distribution with 0 mean, the expectation is 0. Okay, so when you average a lot of 0 mean random variables, you end up being very small. Okay, this is what they average. So it is important that you start your Gaussian descent step from something which is close to 0. And what are the consequences? Then if you simply do like derivations, okay, so this is you find derivatives of that function, then whenever you add one more derivative, you're going to multiply by alpha. Okay, it's the composition of derivatives. So if you take derivatives with respect once, the alpha square over there becomes 1 over alpha. And if you take it another time, the alpha disappears. Okay, so what you're left with is a function, okay, where the Hessian is bounded, because when alpha goes to infinity, this will be small because of my assumption of h being small for W0. This is like bounded Hessian and gradient converging to 0. Okay, so when a function has almost 0 gradient, but the Hessian is bounded, you're almost at the optimum. Okay, so essentially, if you optimize it, there's no need to go very far away. And it's essentially what those algorithms are doing, but those papers are analyzing. They are analyzing situations exactly like that. And indeed, if you do that, okay, you almost don't move. Okay, you stay close to where you are. And close to where you are, you end up having a linear method, okay, which is converging linearly. So you have a linear model. So what do you have a linear model? Okay, let me finish this. You have a linear model because if you don't move so much, okay, you can do a Taylor expansion of your prediction function around the initializer plus the first order term. So at the end, you can see that this is constant with respect to the parameters. This is constant. So at the end, what you're doing is a linear model. Okay, so you're not doing any more non-linearity as a neural network. You're simply doing linear model, which is interesting. And I will explain this in a later slide. But just to show the picture, so this is the same plot as we had before, where you start. This is the mean field regime, where you start with neurons close to 0, uniformly distributed, and you let them evolve, and they converge the good set of directions. If you go lazy, where you blow up the initialization, so that circle over there is the same circle over there. Okay, I had to reduce the scale to make it fit. So you end up with neurons that don't move, okay, along the initialization. And if you take more neurons, they also even move even less, okay, but they don't move much. Just to highlight the fact that if you send the neurons to infinity, okay, then they don't move, and you end up with a result which is an algorithm which is easy to analyze, but not very interesting. So why is it not very interesting? Because, because you don't move too much, you end up with a linear model. And as we know from the year like 95, 2005, and so on, when you have a linear model, there's a kernel hiding behind the scenes. And this kernel happens to be the so-called neural tangent kernel, which is an interesting tool to analyze what neural networks are doing, but only around their initialization point. Okay, so you don't move so much, Okay, and what we have done with Lenaic Chizat is simply highlight the fact that this behavior is due to the blowing up of the scale factor at initialization. So the good thing is that those theories apply to all models, deep and shallow, but the problem is that it's simply a kernel method. Okay, so there are a few questions which I will not cover in this talk because of lack of time. But first question is, does this explain neural networks? Okay, and the answer, you can look at the slides later, is mostly no. Okay, so neural networks are not a kernel method which is like disguised as a neural network. Okay, it's really you need to be able to learn. The neurons need to move. Okay, because the goal of deep learning is really to learn representations. And here, by just using like random initialization and in our models, just doing like a random feature, which is good, but not doing any form of representation learning. And of course, can you make those kernel methods beat neural networks? And the answer at the moment is not really. I wish it was true, but I think there are more and more work trying to tie the performance of kernel methods and neural networks. So let me skip that. And let me, since I have like 4 minutes left, try to like one slide on the healthy interaction between like theory, application, and hypes. So as you can see, like people with this like burst of activity on archive and with like social networks, they tend to overhype the research. Okay, so the question I would like to answer now is, should or can learning theory resist deep learning? So first, I think that learning theory should not resist deep learning in the sense that if those methods are working very well, we cannot ignore them. Okay, the goal of theory is first to understand what people do in practice and to propose extensions, okay, to be a guide to practitioners. So we cannot simply ignore what's being done, because that would be not very wise. But I think we should not lower the scientific standards. Okay, and this is like, to me, quite important, and this is true both for empirical research and for theoretical research. When you do like experiments, it's hard to be rigorous, okay? And people know how to do it, but sometimes by lack of time, lack of resources, they're not rigorous. So for example, like validation, testing sets are very important and sometimes get forgotten because of lack of time. Error bars and results get forgotten now because I have to run 10 times. I don't have the money to do it or don't have the computer to do it. Sure, but without error bars, sometimes it's hard to assess if you're doing really better than the other algorithm. So this is very classical, and we have this so-called reproducibility crisis starting a bit in machine learning. So we're not there yet, but we're getting close where results get harder to reproduce. And I really encourage you to be really careful in the validation, training, and testing frameworks. But this is true as well for theory. Okay, so for theory, sometimes people follow the hype and tend to over-market their research. And the good thing with theory is that assumptions are explicit. So at least you cannot hide behind anything. So I think this is good that we have assumptions that are explicit. But here, it's difficult now to do research in theory because it is unlikely that we're going to get soon like results as precise as for SAG or convex optimization, where give me your budget in number of iterations, budget in number of neurons. I will tell you how good your network will work on future data. I think we're very far away from that. And this is where I think we could like learn a bit from physics, which is the field used with very complex systems. So their systems are typically not built by engineers, okay, like ours. They are built either by engineers or by nature, but they know how to extract some small pieces, analyze the small piece, get some guiding principles that will be helpful for everybody. And I think this is something we could follow. And since we talk about physics, I like to highlight, give some wisdom from physics. So this is like on the website of the journal Physical Review, which is an important journal in physics. And this is a guide to authors. So I'm not going to read it, But essentially, please read it. And but the aspect here is that it's about claims of novelty. Okay, so now if you look at regular nearest paper code or ICML, and probably in my papers as well, we tend to overemphasize novelty. It's a first, it's a new, it's like often like superlatives about your own work, and I think this is not needed. Okay, and I think that those type of guidelines are important to avoid like overselling. Okay, we should not undersell, but I think we tend to oversell too much and lose exactly what we should do. So to conclude the lecture, so I've presented like two setups: the convex case with a single machine where things are quite well understood. And now what you have is matching low one upper bounds for either LGD on the testing error or variance reduced techniques on the training error. And this is quite well understood. What is not well understood, and what are quite a few, like many open problems, is like step size schedules. Okay, so this was mentioned already. So I think this is like difficult, but quite open. So acceleration, of course, this is always like, you always want to accelerate. So of course, non-convexity. So I've tried to present like early results, which are very far away from the complete picture because you are missing quantitative results essentially. And of course, still in the convex world, this remains open. Distributed learning remains interesting because this is really what driving force, because okay, you cannot, you have more and more data sets, you have more and more computers, so you need to make them work with each other. Thank you for your attention.
Yep. Thanks, Francis, for such a nice talk. Now, do you think you can take some questions, or do you want to take those in the round tables?
I think I can take a few ones now. Yes.
So there was this, what is your opinion about Langevin dynamic interpretation of SGD by Kshitij Patel?
Okay, so here I think the Langevin thing. So here the devil is in the detail. Okay, so if you do Langevin to do sampling of some log density, sure. So and this is totally fine. But the detail is that when you do Langevin, so you do like theta t is theta t minus 1 minus gamma times your gradient plus some noise. But for Langevin, the noise has to be multiplied not by gamma, but by square root of gamma. So when gamma is small, square root of gamma is much bigger. Okay, so to do sampling for Langevin, you need to really blow up the noise. Whereas if you analyze LGD, the noise that you add on the gradient is multiplied by gamma, by the same step size. Okay, so typically when you want to analyze to find the continuous limit of LGD, you would tend more to the gradient flow because you add the noise contribution goes to 0. Okay, so this is how it was done in the 80s, proving LGD through the gradient flow. But you can also add Langevin to analyze a different problem. This being said, you can leverage techniques from Langevin. Okay, so I've done some work with Émeric Delveux and Alain Durmus, where we leverage techniques from the Langevin world back to the LGD world. Okay? But to me, Langevin is not the proper model. It's very interesting, but not the proper model for LGD.
Mr. Last, is there any extension of the Markov chain framework that allows analyzing the asymptotics of non-constant step size algorithms in a similar way?
I think that we leave it open. So in the paper with Alain Durmus and Émeric Delveux, we leave it open, saying that it can be done, it should be done, and I don't know, but it's a lot of math. But clearly, you could have something where this can be done, of course. Yeah.
So Kshitij asks again, what about language problems where the observations are virtually infinite, but neurons are not? How does our parameterize affect those problems?
That's a very good question. I don't know, but okay, so I don't know. But you could imagine that, so we should not forget our kernel knowledge. So even when your inputs and your parameters live in infinite dimension, as long as the dot product is finite, and probably for NLP, the infinite size, I think, also comes with sparsity and a finite amount of energy on all observations. So I think this could extend, but of course, in principle, okay, so a lot of things has to be done to take this into account, but I don't see any major issues there.
Can you comment on the connection between the main insight of viewing average as measures versus, say, your work on kernel herding? Okay.
That's a very okay, so in kernel, in a herding, so what we're trying to do, we are trying to approximate measure. Okay, so difference. Okay, the difference. So herding essentially, this is the Frank-Wolf part that I've mentioned. Okay, so when we are trying to learn a big measure by seeing at the convex combination of extreme points of our convex set. Okay, so we are trying to reach a good set of extreme points. Okay, in what I'm doing here, the extreme points are allowed to move. Okay, I start with a fixed amount of extreme points, and they move around and adapt to the correct place. Okay, so I do believe this is a core difference. When you do Frank-Wolf for herding, which is the same here, you add extreme point one after the other, and they don't move; they are fixed forever. Whereas in the particle framework, they move all along, and typically moving will adapt much more than having a fixed thing, because if you're in a very high dimensional space, in particular, if your convex set is a convex hull, but it's not a polytope, so it has like smooth boundaries, as soon as you add a neuron, it's not good anymore. You want to change it, you want to change it a bit. When you have a polytope and you add an extreme point of a polytope, you can't change it because it's stable as an extreme point. So Frank-Wolf algorithms for polytopes are great because typically the new atom that you add does not move, does not need to move in the next iterations. If you live in continuous boundaries, you need to move everything, and this is okay. It's a hand-waving explanation, but this is to me why you need the to have particles. It's a bit better.
Okay, so Michelle asked again, do the Wasserstein gradient flow results have implications for modifying particle filtering and more general Bayesian inference approaches?
It's a good question, but I don't know. I know that, so I'm not the expert there. This is more Lenaik, my co-author, is the expert there, but indeed the certain gradient flow, okay, so you have classical ones, okay, and probably I know that there's somewhere by Umut Simsekli trying to do something like this for particle filtering or for sampling, but I forgot, I don't know the details.
So yeah, we have two more questions.
Yeah.
If you are willing to take it now.
Two, and then I can have a break. Yeah.
Okay, perfect. So one is, do you have intuition about how our parameterization lets gradient flow escape local optima?
How
our parameterization lets gradient flow escape local optima?
How?
Yeah.
I think also okay, we have a proof. Okay, so the proof essentially, this is like, I think during the roundtable yesterday, I've mentioned that Yann Lequin kind of picture where if you're in a local optimum, okay, to go out, you have to go above like some barrier. And if you add many dimensions, you can go around and do something like this. And essentially, the way the proof works is that whenever you start to be stuck in a stationary point, there's always a direction of descent appearing because you have a direction where you can escape the stationary point. So the proof relies on that. but it's I know it's a bit imprecise, but there is no. I've tried. We've tried with NIC to get the intuitive explanation of how this works, but this is difficult.
So the last question by Miko: is the connection of a single layer network being equal to a Gaussian process on the limit in the number of units useful, interesting in this context?
That's a good question. So it's useful in the sense that if you generate random neurons, okay. So let me add back. Let me put this easier. So if you take you take your neural network over there. Yeah, so you generate randomly both the input neurons and the output neurons. Okay, so what this Gaussian process interpretation will tell you is that if you put them at random here and then let them fixed and only optimize over the second layer, you're doing exactly a kernel method. Okay, so it's formally equivalent to a kernel method. If you let the number of neurons go to infinity, and those are random and fixed, you're just doing a Gaussian process or kernel-rich regression, whatever. But the problem is that this is just a kernel method where the set of features do not adapt. Okay, so you do them randomly. Okay, they can't adapt to the specificity of the data set. What neural networks are doing and what this analysis is doing is that we generate everything randomly first, those ones and those ones, but we optimize all of them. Okay, so those neurons are adapting to the specifics of the distribution. So this is what I call representation learning. You learn features, okay, and that feature learning allows you to have like fewer neurons, okay, and you can show. So I have a paper 2 years ago showing that you adapt more if you can learn the neurons. Okay, so this is really important to learn both the output layer and the input layer. And so the Gaussian process interpretation is good to understand what's happening if you optimize only over the second layer. And the neural tangent kernel, which I was mentioning, is doing something which is similar to what I've mentioned. So there's a bit more features, but it corresponds essentially to random features.
Okay, so yeah, we see you again at roundtable in approximately 15 to 20 minutes.
Okay, very good. All right.
Okay. Thanks, Francis. Thanks for this amazing talk, and thank you all the attendees.
Yep.
Bye.